Dear students, so welcome to the first tutorial of digital communication. So today we will have no video lectures, but on the contrary we will just go through some problems related to the material that you have learned so far, and I will give you the solutions also, but I will ask you to try the solution first and then I will discuss the solutions, okay, so that you can learn by doing. So let's proceed. So the first problem here is based on binary symmetric channels. So what we are having here is we have two binary symmetric channels. So this is the binary symmetric channel 1, okay, and the output of this binary symmetric channel 1 goes to the input of channel 2, and then finally we have the outputs y0 and y1. So given x0 and x1 and all these transition probabilities, okay, so for channel 1 the chances of getting an error is PE comma 1, and chances of getting a symbol correctly is 1 minus PE comma 1. For channel 2 the same parameter is PE comma 2, and these values are given in the problem. You have to find out the transition probabilities of the combined channel. So let's imagine that this is equivalent to a binary symmetric channel where you have x0 and x1 as input and you have y0 and y1 as output, and let's say you have 1 minus PE and PE, and then here also you have 1 minus PE and PE. Okay, so these are the parameters of the combined channel, and you are asked to find out this PE, okay, which of course PE is a function of PE1 and PE2, okay, which are the individual channel transition probabilities for channel 1 and channel 2, okay. So I will ask you to solve this problem yourselves and then I will give you the solution, okay. Okay, so here is the solution. So because the channel is further on symmetric, the consideration of one error case is sufficient for the determination of the error probability. So basically what does that mean is that, let's say you have the combined channel whose input is x0 and x1, and you have here y0 and y1 as your output, then basically the probability of error or probability of getting the bit flipped is PE, and 1 minus PE is the chance of getting them received correctly. So actually your PE is the conditional probability. Let's say if you imagine the transmission of x0, okay, and you are receiving y1, so that encounters for this PE. So PE is basically the conditional probability that you have received y1 given that you transmitted x0. Okay, so if you can calculate this, then by symmetry of this channel, okay, the combination channel is also binary symmetric. So by symmetry of this channel, you can say that this is also equal to probability of y0 given x1 was transmitted, and the other probabilities are just 1 minus this term p. Okay, so if we calculate one, then we know the others. So let's see what is the probability of y1 given x0. So if you now look into the breakup of this channel into two, so this one was your z0 and z1, and then you have y0 and y1. So let's say probability of y1 given x0 can happen in two ways. Let's say your x0 was transmitted, okay, and then you obtain z0 at the intermediate channel, and then you have y1, or you obtain z1 at the intermediate channel and then you have y1. Okay, so you can have either this possibility or this possibility, and then these are the two probabilities for these two possibilities. Okay, so let's say probability of y1 given z0 at the input of the second channel times probability of z0 given x0. Okay, so this arm and this arm are given by these two probabilities, so they are independent, so you are multiplying them. Similarly, probability of y1 given z1, so this arm multiplied by probability of z1 given x0 is this arm, so that gives the probability of this path. So this is this term, and now all these probabilities can be written in terms of P2 and P1, and these values are given to you, so you can easily calculate by replacing P1 as 0.01 and P2 as 0.02. The final value will be almost equal to 0.3. So that will be your combined channel. Okay, so x0 will be received as y1 with the probability 0.3, and x0 will be received as y0 with the probability 0.7. Similarly, x1 will be received as y1 with a probability 0.7, and x1 will be received as y0 with a probability 0.3. So that's the final answer. Okay, so let's move on with the second problem. So let's say we have a received signal in the binary communication system that employs antiportal signals. Okay, so antiportal signals means that you have, when you have, let's say 0, you have minus of st, and when you have 1 you have st. So this is actually your antiportal signaling, as you have already learned from your lecture notes and videos. So this is let's say the received signal is st plus nt, okay, where nt is the noise, with AWGN and power spectral density N0 by 2. And ST looks like this. Okay, so basically you are sending ST and minus of this when you have a 0 and a 1. Sketch carefully the impulse response of the filter matched to ST. Then next part is sketch carefully the output of the matched filter when the input is ST. Determine the variance of the noise at the output of the matched filter at t equal to 3, and then determine the probability of error as a function of A and N0. Okay. So again, I would request you to try solving this problem, and then I will give you the solution. So let's look into the solution one by one. So the impulse response of the filter matched to ST. So ST was looking like this, right? So it had an amplitude A, and you have 0, 1, 2, 3, okay, like this. Yeah, so this was your ST. Now, from your discussion of matched filter, from your lecture note, if you recall, that a matched filter HT that was matched to, let's say, phi 1t. Okay, so you had two arms in the receiver, and you had, let's say, two matched filters. Okay, one was matched to phi 1t and the other was matched to phi 2t, and then you are sampling them, and then the next part goes to the input of the decision device. Okay, so phi 1t, what was the matched filter that was matched to phi 1t? That was basically phi 1 TB minus T, right? So that was the theory that we went through. So you have to apply that concept here. So TB was the bit duration. Okay, here your bit duration is capital T, let's say. Okay, so this is your capital T. So basically the matched filter matched to ST is nothing but S of T minus T, same as this concept. And you can see that the bit duration here is 3, because this is the entire signal that you are sending for a duration of a bit, right? So essentially this is the duration from 0 to 3. This is the duration of a bit, because the signal that you are sending is defined over a bit duration. So in this case your bit duration TB is 3. Okay, so that is what we are using here, S of capital T minus T, or TB minus T, anything, you can use any notation. So that is your S of 3 minus T. Okay, and if you look into this signal carefully, this is your ST. S of 3 minus T, if you plot, then from the structure and symmetry of this signal you will see that S of 3 minus T exactly looks like ST. So therefore the impulse response of the filter that is matched to ST is basically ST itself. And the reason S of 3 minus T equal to ST is because ST is even with respect to the T equal to capital T by 2, that is 3 by 2 axis. So if this is the 3 by 2 axis, then this is symmetrical and even with respect to this. So that's why we have s of 3 minus t equal to st. So this concept is directly from your signals and systems module which you studied last year. So we have ht equal to st. So now the output of the matched filter is nothing but yt, which is equal to st convolved with ht. Since your ht is equal to st, so basically you are convolving st with itself, okay. And if you do that, then you will get these expression. Now you can see this is a bit complicated. This is a piecewise linear function defined over different intervals, okay. So how do you actually get this from this? So one way of doing this is that you can have st convolved with itself is basically in the frequency domain. You can take everything in the frequency domain, okay. Let's say you have the Fourier transform of yt, which is yf, and let's say the Fourier transform of st is sf. So yf is basically this term, okay. So therefore it is easy to work on the Fourier domain. So you look, st is basically the sum of two square pulses at between 0 to 1 and 2 to 3. So you can write this as an equation of two square pulses, okay. So your st is basically ut minus u of t minus 1 plus u of t minus 2 minus u of t minus 3, okay. And then you can take the Fourier transform of these, okay. And I'm not going through the details of this. So if you take the Fourier transform of this, you will basically get sinc function. So this is a square pulse, and the Fourier transform of a square is a sinc function, right? So you will get sinc functions, and if you square that, then you will get some expressions which will be in terms of sinc square, okay. So this will be some series of sinc square functions, okay, plus something, another sinc. So again, I'm not giving you the details, you can work this out. And if you do the reverse transform of this sinc square, okay, you will basically get, so again from your signals and systems class, the reverse Fourier transform or inverse Fourier transform of sinc square is basically a triangular shaped function like this, okay. So you can see that this function, basically whatever it is given here, is actually three triangular functions that are centered around t equal to 1, t equal to 3 and t equal to 5, okay. So the way you write this in terms of equations in time is this. So basically between t equal to 0 to 1 you have one side of the triangle, between 1 to 2 you have another side of the triangle which is given by this, and the amplitude here it starts from t equal to 0, and the amplitude here is a square, okay. Then the next is between 2 to 3 you have a bigger triangle whose amplitude is twice a square, so that triangle is between 2 to 3 and 3 to 4, so you have a bigger triangle that is centered between 3 t equal to 3, this is 1, and then you have another small triangle given by this portion which is centered around t equal to 5. Okay, so if you work this out carefully, start from st, take the Fourier transform, you will get a sum of sinc functions, square of that will give you a sum of sinc squares, and then you reverse Fourier transform that to get these three triangular functions. So basically you will get yt, which will look like this, that is clearly given in this slide, and the expression of yt would be like this. Okay, so so at the output of the match filter for t equal to 3, the noise will be calculated as this. Okay, so basically you are convolving the noise with the matched filter, and the matched filter itself is st, so you have eventually this expression. Okay, so now if your noise is this integral, then the variance of noise is basically the expectation of multiplication of two such integrals. Okay, so you can write that in this form. Okay, and then you can calculate the variance of the noise, okay, by doing some algebraic manipulations and applying the rules of calculus, as well as the property of the noise, which is Gaussian zero mean. You will eventually end up with this expression, and then you find this part is basically the energy of the signal, which is a square, so you will have 2 a square, so you will have n0 a square. Okay, so that is basically your answer to part C, which is asking you to determine the variance of the noise. So the variance of the noise is n0 a square. Now for antiportal equiprobable signals, the probability of error is like this. You have seen this in the case of BPSK. Okay, so now you can calculate this signal to noise ratio. So that is basically your signal term, which is the output of the matched filter. Okay, that was yt sampled at t equal to t. So that you have calculated in part B. Okay, so basically you have square of that term at t equal to capital T, that will give you this term in the numerator, and the expectation of the noise, I mean the variance of the noise, which you just calculated, is this. So basically this will be the q of square root of 4 a square by n0. Okay, so that is your final solution. So let's look into the next problem. Let's look into problem 3. So problem 3 basically says that you have a signal, you have a binary communication system that employs these signals. Okay, you have S0, which is equal to 0, and you have S1, which is equal to a constant amplitude. Okay, so this is an example of on-off signaling. Okay, so this is similar to the BASK that you have seen. Okay, now the demodulator cross correlates the received signal RT with S1T and sample the output of the correlator at t equal to t. Determine the optimum detector for an AWGN channel and the optimum threshold, assuming that the signals are equally probable, and find the probability of error as a function of the SNR. Okay, so the first thing is that if you look into the energy of the signal, so the energy of S0 is 0, and the energy of S1 is basically um, this term. So this is a square t. Okay. So basically, you can see that this from this you can see that this can be same. This is same as BSK. So this can be represented by a single direction phi 1, where you have 0, and here you have square root of S1. So S1 S0 is 0 and S1 is here. So this is your S0 and this is your S1, and this amplitude is given by the square root of energy of S1, and that is nothing but a root t. Okay. So when in the demodulator you are correlating the received signal with S1 and sample the output of the correlator at t equal to capital T, which is the bit duration, then essentially you are getting these samples. So basically you are getting R equal to Sm plus N, because your receive signal is A plus Nt when you are transmitting S1, and just the noise because S0 is 0. Okay. So you have R equal to Sm plus N, where M can be 0 and 1. So in case of M equal to 0, you have S0 equal to 0. Okay, because according to the signal space representation, this is 0 and this is a root t. So this is S1 and this is S0. And in case of M equal to 1, therefore your S1 will be a root t, and then the noise sample, whatever is that. So the noise variance can be calculated like this. So basically you are multiplying one sample of the noise with another and integrating them. So basically you can simplify this as this expression, and then this can be replaced like expectation of nt multiplied with n tau is nothing but n0 by 2 delta of t minus tau. Okay, so you replace this here, n0 by 2 comes outside of these integrals, and then you have this remaining integral. So the area under this will be capital T. So then the final answer is n0 by 2. Now the probability density function for the sampled output will be like this. For S0, given S0 was transmitted, the received signal will have a conditional PDF, which is a normal distribution with 0 mean, because your S0 is 0. In case of the conditional density of the received signal R, given S1 was transmitted, you have a mean that is centered across the energy, the amplitude of S1. Okay, so that is here a root t. So R minus a root t square in the numerator here. So then your optimum decision rule is basically to detect whether this term is greater than this term or not. Okay, so basically this comes directly from the lecture notes that we covered previously when we were trying to define the optimum decision rule based on the minimization of the probability of error. So we saw that we have this likelihood ratio, which is the ratio of these conditional PDFs, and in this case the likelihood ratio calculates like this. So all we need to do is to verify whether this ratio is greater than or less than 1. Okay, so So in other words, we if we take the logarithm of two sides, we get this value. Okay, and the threshold is basically given by this term. Okay, so you are essentially trying to find out whether your received signal is greater than this threshold. If that is the case, you decide S1 was transmitted, and if less than this, then S0 was transmitted. And this indeed is true if you look into the signal space diagram. So your S0 was 0 and your S1 had an amplitude of A root T. So the optimum decision threshold will be a perpendicular bisector of the line joining the two signals, and this would roughly be at a distance, not roughly, actually exactly at half of A root T. Okay, so this is what is happening here. You have this, which is giving you that the threshold is the received signal that is greater than or less than this term. Okay, so now if you calculate the average probability of error, then that means you have, so the two signals are equiprobable. Okay, so probability, the a priori probability of S0 and a priori probability of S1 is half each, because you have two signals which are equiprobable. So equiprobable. So equiprobable means that you have PS0 and PS1 as half. So therefore, this PE, this is basically PS0 times the probability of error due to S0 plus PS1 times the probability of error due to S1. And these two are half, so we start with this half, and then you have these conditional probabilities. And the conditional probabilities are nothing but the integral of this PDF from the threshold to infinity and minus infinity to the threshold. So if you look again, so this is your threshold, which is half A root T. This is your threshold, and here is your signal S1, here is your signal S0. Okay, and so so probability of error due to S0 is basically this area, and probability of error due to S1 is this area, and this area is basically from here to infinity, so half of A root T to infinity, and this area is minus infinity to half of A root T. So we are just applying the concepts that we have learned so far. And if you now work this out, these integrals, so you will find that you have q of this function, which if you define the SNR as this, which is the total or rather the average signal energy. So average signal energy is basically E of S0 plus E of S1 divided by 2. So E of S0 is 0, E of S1 is A squared T, so this will be half of A squared T. So that goes in the numerator, and in the denominator you have N0. So you have your SNR as this quantity, half of A squared T by N0. So this term inside the Q function, the argument of the Q function is basically square root of SNR, where your SNR is this quantity. So thus the on-off signaling requires a factor of 2 more energy to achieve the same probability of error as antiportal signaling. So that's the solution here. Okay, so we will stop here with this tutorial, and then I will see you in another video.